Perfect, thanks. All right, hi everyone. I'm Deborah Good, and as Terry said, I'm a postdoc at the University of Connecticut and the Flatiron Institute Center for Computational Astrophysics. And today I'm going to talk a little bit about the IPTA in the era of the ngVLA and SKA. Except really, this is a secret talk about the ongoing work on IPTA DR3 and about pulsar timing arrays in general, because I think what we're doing now is really foundational to what we'll need to do when we're looking at an SKA era IPTA. Okay, so first, in order to understand this, we have to talk a little bit about pulsars and about pulsar timing. It wouldn't really be a radio astronomy conference if nobody talked about pulsars now, would it? So the pulsar is what's left over after sort of a medium-sized star dies. It's a rapidly rotating neutron star. These are very, very dense objects. We're talking about masses around 1 or 2 solar masses, but radii that are only like 10 or 20 kilometers. It's about 10 kilometers from downtown Vancouver to the UBC campus, for reference. The pulsar also has really high magnetic field, anywhere between 10 to 12 and 10 to the 14 Gauss, depending on exactly what kind of pulsar you're dealing with. And they also have a wide range of spin periods, everything from about a millisecond and a half all the way up to, I just checked, the current longest period neutron star pulsar is 76 seconds. These sources, we call them pulsars because they look to us like they're pulsing, but they aren't really pulsing. What's really happening is, like in this diagram on the right-hand side here, you have an axis around which the pulsar is spinning and an axis along which there's a beam of light. And those axes don't align. So from our perspective, it looks like the pulsar blinks on and off at its spin period. But what's actually happening is that it's just moving around like a lighthouse. So we're specifically interested in the pulsar timing array community in millisecond pulsars, which are pulsars that started out as normal pulsars, and then they had a companion. They accreted material from its Roche lobe, and they spun up. They are now spinning much, much faster than the average pulsar. If you actually do the classical mechanics math, you do not get a number anywhere near 1.5 milliseconds for a potential neutron star or potential pulsar. The way you get a really fast spinning millisecond pulsar is by having this recycling process. One of the things that's really important is when we have these recycled pulsars, they become very, very stable timers. Pulsars do lots of interesting things, but millisecond pulsars are very, very steady. We can predict when we'll see pulses from them with an accuracy on the order of 100 nanoseconds over 10 years for the most stable ones. Oops. So what we're doing in pulsar timing arrays is pulsar timing. We're observing the pulsar for a long period of time, i.e. many epochs. We don't need a long observation at each epoch, but we need to be taking data for a long period of time, i.e. years. Each time we take data, we determine a time of arrival. That's sort of our core data point for each observation. We fit a timing solution to the total set of data, which is really just a very large model fitting problem. And then, like you always do with a model fitting problem, we look at the residuals and we see what's left in the residual and try to remove as much structure as we possibly can. What are some of those things we actually see when we time pulsars? Well, I like to split it up into 3 different places where the thing can be happening. First, there's things that are related to the pulsar itself. That's things like the spin period derivative. Many of our MSPs are in binary, so then we have both classical and relativistic binary elements. Binary orbital elements. And we also, for some of our best time pulsars, get to do kinematic perturbations to those orbital elements. There's also things that happen because we're observing the pulsar from Earth, which is a specific place. It has our uncertainties in position, things like proper motion and also parallax, which we can measure with timing solutions. And there's also things that happen because the only things in the universe are not the Earth and the pulsar. And that's primarily something we call dispersion measure. So in the interstellar medium, there's lots of ionized gas. And when light from the pulsar passes through the ionized gas, the pulse is dispersed or slowed down in a frequency dependent way. So your high frequency light arrives before your low frequency light, even though it was all emitted at the same time. And for a pulsar, you have some nominal dispersion measure or DM that's the value for that pulsar. But when we're doing high precision pulsar timing over a long period of time, we also have to care about time dependent variations. And this is actually one of the trickiest parts of doing pulsar timing, is modeling these very small time dependent variations in dispersion measure. Relatedly, we also see the same kind of dispersion happening from things like solar wind and when the pulsar potentially passes behind the sun or goes near the sun. So there's a lot of different parameters we're trying to deal with. And here's what we get at the end. So this is the top left plot here is from the second International Pulsar Timing Array data release, but I just thought it was kind of graphically ugly. So I also included a plot, a very similar plot of the same pulsar from the Nanograv 12.5-year data set. This is pulsar J1744 minus 1134. And what you have here on the x-axis is time in years. So this plot ranges from 2004 to 2018, the large one. And on the y-axis is residuals in microseconds. So your top panel here, that's your range is between -20 and 20 microseconds. And you'll notice it looks like there's little columns of data each time there's a data point. That's because when we calculate times of arrival, we calculate them for small portions of the total frequency band called subbands. The next two panels, we've averaged across all the subbands to get just one data point per observation. And that actually brings that range of residual all the way down from -20 to 20 to about -2 to 2. You'll notice the second plot, this averaged residual, doesn't necessarily look quite right. There's a little bit of a wobble around 2015. So we are also able to find, in addition to the sort of very physical, simple to explain model fitting, we also do more complicated Bayesian model fitting to look at white and red noise parameters. And the final plot shows after individual pulsar red noise parameters have been applied, we go from having that little bit of a wobble around 2015 to having our residuals nice, flat, and white, which is what we want. Now, it's important to note that is a single pulsar red noise model. That is something that is specific to this source. That's not for the entire pulsar timing array data set. The reason why that's important will become clear in a minute. So we are going to use these pulsars in pulsar timing arrays as gravitational wave detectors. That's the reason why we care about pulsar timing arrays, or at least one of them. And where does that fit into the picture? So just like the electromagnetic spectrum, there's a gravitational radiation spectrum ranging from things at high frequency, short periods, so things that you have to see it or you miss it, seconds, minutes kind of time scales, like LIGO. And that's detected by that's detected by ground-based interferometers like LIGO. You're mostly looking at stellar mass black hole mergers. In general, the higher frequency your gravitational wave, the lighter the object that created the gravitational wave. In the middle, we have we look forward to the era of LISA, space-based interferometry, where you'll have arm lengths about the size of the Earth, in contrast to LIGO's couple of kilometer arm lengths. And here you'll be finding much bigger binaries, potentially supermassive black hole binaries, and also extreme mass ratio inspirals, where something stellar mass is going into something supermassive. And finally, the part we're concerned about when we talk about pulsar timing arrays are these low frequency nanohertz gravitational waves. And here we're primarily looking at the stochastic background, tracing out the history of supermassive black hole mergers in the universe, and also looking at the in-spiral phase of supermassive black holes as the two black holes are moving together. And that's what we'll be able to see with pulsar timing arrays. So scientifically, you have two big supermassive black holes. They're in a binary and they're spinning around each other. And this is what actually creates your gravitational wave. It basically stretches and squishes the fabric of space-time. And when it does that, it causes changes in when we see the time of arrival from the pulsar. So some of our pulsars appear to show up early, some appear to show up late, and that's done in a spatially correlated way. Because we have such high precision information about when we should see times of arrival from that pulsar, we're able to say, okay, something is happening here, and that something is a gravitational wave. Specifically, we do this by looking at millisecond pulsars for a really long time. And we're looking for two things to say we have a gravitational wave: a common spectrum red noise process, so not an individual pulsar red noise process, but a red noise process in all of the pulsars, and also a Hellings and down spatial correlation, which is just that stretching and squeezing. It has an analytical shape that makes a plot like the one on the right. So have we actually seen gravitational waves yet with pulsar timing arrays? Not quite, but we are optimistic that this is something that's on the horizon for us. So each of the regional PTAs that make up the IPTA, as well as the IPTA itself, have reported common red noise processes. So that's step one of finding a gravitational wave, but not the Hellings and down spatial correlation. So we're not able to say we've seen gravitational waves yet, but we're optimistic that this is something we'll see soon. We would expect this signal to grow over time. Okay, so let's dig into the nuts and bolts a little bit of the IPTA now that we've talked about what a pulsar timing array is and why you do it. So this is all of the groups and the telescopes that are involved in the IPTA. There's NanoGrav, or the North American Nanohertz Observatory for Gravitational Waves in the US and Canada. There's the European Pulsar Timing Array in Europe. There's the Chinese Pulsar Timing Array in China. There's the Parkes Pulsar Timing Array in Australia, the Indian PTA in obviously India, and also newly the Meerkat PTA in South Africa. And in the long run, we expect to add SKA to this as well. If ngVLA ends up doing pulsar observations in a way that would be helpful to us, we'd love ngVLA data too. But we think our focus for the next gen is going to be the SKA. So the idea here is that if one PTA, if any of these individual colored blocks of regional PTA are good, then having more PTAs is even better. We can combine data from each of these groups to create a giant PTA. And as of right now, this is something that is expanding rapidly. So the plot on the bottom right here shows in blue and red the DR1 and the DR2 points from the previous data releases. Our previous data release, DR2, had 65 pulsars included from just NanoGrav, the IPTA, and PPTA. In DR3, I just rechecked the math, and with the inclusion of Meerkat, we're going to have 115 total pulsars included in our PTA, with 5 different groups at least. So we're very excited about this. This is going to really expand the IPTA, and this is going to be a really important test site for thinking about what it's going to look like to do pulsar timing array science in the era of the SKA, by having much larger data sets, by having a lot of telescopes, and hopefully that'll improve we expect that to improve our sensitivity. Why will it improve our sensitivity? Well, it's actually fairly straightforward. We have this scaling law for the probability of detecting a gravitational wave. It varies directly with the number of pulsars and with the square root of the observing time. What that means is that the more pulsars you have and the longer you observe them, the better your sensitivity to gravitational waves. And in particular, you're actually more influenced by the number of pulsars you have. So provided it doesn't kill you from a personnel perspective and a compute resource perspective, it's to your advantage to include as many pulsars as you can, like we're doing with the inclusion of Meerkat and the future inclusion of things like the SKA. There's just one slight problem, and that is that actually getting to a data set from all of these different observatories is really difficult. It's very non-trivial, and it's a lot of work. So this is where we start to think about some of the specifics of how we're preparing now to do better and more efficient IPTA data sets. And here's a few of the points we've come up with. One is to build a team. So previous data releases have been done by very small teams, like on the order of 1 to 3 people. We realized that as we build into 115 pulsars now, and who knows how many pulsars in the SKA era, we're going to need a lot more help than that. It's going to be too big for any small set of people to do themselves. So now I'm one of the co-chairs and one of the leaders of the DR3 data combination team. There we are on the bottom right in New York City this past fall. We're also building a new pipeline. We're thinking about how if we have more people, we also need to have something that is easier to learn. And we also, as we get into more, as we think we might be on the verge of a detection, we want to make sure we feel good about the pipeline itself, make sure we feel like our science is reproducible and it is well motivated. So we're trying to make an easy to learn, easy to modify, best we can possibly do pipeline. One of the ways we're doing that right now is actually by having parallel pipelines. So we have one pipeline that is Pint, which is a Python-based timing software based, and the other is Tempo2, which is a C-based pipeline for timing. And there's advantages and disadvantages to each. And right now we're leveraging the fact that we have an international group with many different software expertises to build these parallel pipelines. We're also being much more intentional about how we manage our data. We're getting up to speed with things like GitLab that'll let us check in and out different solutions and keep on top of what's happening among all the PTAs. And we're also developing some new science tools. The process of modeling these dispersion measure variations has always been a big problem for the IPTA. And we're working on a new Gaussian process format that we're pretty excited about. So this is very preliminary, but I do want to point out this is working. This is a recent combination of J1744 minus 1134, the same pulsar we saw earlier. Here, the blue is the European Pulsar Timing Array, the red is Parkes, the green is NanoGrav, the purple is Indian PTA, and I want to draw special attention to the orange, which is Meerkat. It's beautiful data. You'll hear more about it in a few minutes. So we're excited to see all these PTAs on one plot and looking, in about the right order of residual size. We're also really excited about this new Gaussian process-based model. I don't have time to go into this in depth, but this is a relatively recent result from a University of Connecticut graduate student, Bjorn Larsen, comparing in orange our new Gaussian process DM model to in black the piecewise constant DMX model that Nanograv has been using. And what you see is it largely reproduces the same structures. And it's a lot more flexible. It lets us include information from every possible type of TOA, which has been a challenge in previous iterations. So to summarize, pulsar timing arrays are on the verge of detecting low frequency gravitational waves. We're in this new golden age of radio astronomy, and that's going to be a huge boon for PTAs, but it's also going to mean there's scaling up related challenges. We're using this current third data release to start meeting those challenges by building software tools, by building a team, and by doing even better science. So I'm happy to take questions, and thank you very much.
Thank you, Deborah. We have 5 minutes for questions. All right, Weil and then Ziggy.
Who is that? Thanks for the talk, Deborah. My question is, in the era of SKA and more sensitive radio telescopes, are we going to hit a limit in terms of jitter noise from the pulsar itself? So are we not anymore limited by sensitivity and limited by the tool, which is the pulsar that we're using in PTAs?
I think there's a definite risk of that. I think jitter noise is going to be something we're going to talk a lot more about in the sort of DSA 2000 SKA type era.
Nice talk, Deborah. I was wondering, in your sensitivity equation, there must also be something for the sort of the baseline over which you time the pulsars in there. Could you comment on that?
Yeah, actually, that's what that T in there. Hold on a second. So in the scaling relation, and this is from Siemens et al. 2013, it's the number of pulsars times the square root of the T observed here is the length of time you've been observing for.
Oh, so I couldn't not do it like if I do 10 hours today, that's not what's here, but it's like over.
Right,
over
it's how long you have been looking at because when you're doing a pulsar timing fit, you need to have, it's the same principle as when you're doing like a Y. I know Ziggy knows this, but people probably don't know this. It's the same principle as when you're doing like a basic Y equals MX plus B fit, where like it's really helpful to you to have data points that span a wide range, because that gives you much more constraint on your fit than if you have a bunch of data points clustered in one tiny place and you're trying to predict what'll happen, you know, many points down the line.
Okay, yeah, that makes sense. So I guess if we turn on SK and we detect pulsars, we still have to build up the baseline before they become really useful for PTAs.
Yeah, we benefit from the fact that SKA is going to see all of those 115 pulsars I'm talking about for DR3. And so we get the timing baseline from having had all of these other PTAs, but it will continue to get better and better as we get more time range on SKA. One thing we're actually wrestling with right now in the IPTA is at what point in time do legacy data become so inferior to current data that they're actually dragging you down? And I think that's going to be another big question in the SKA era.
Okay, Adam, and then over here. Hey, you want to go first? You had your hands up.
Thank you, Deborah. I'm very interested in the DM modeling. How do you know, well, the DM modeling tells you something about the interstellar medium. So how do you know you're not overfitting, when you're doing these Gaussian processes?
I would say that is my number one concern with this method. I think that's something we're still trying to understand. How do you make sure you're not overfitting? And I think, these are wonderful questions, because you're all managing to ask about like the biggest open questions in the IPTA. And I think one of the reasons why we're doing a parallel pipeline right now for noise modeling as well as timing is to enable us to check and see, like, did we do something really, really overfit in that noise model, and we shouldn't go forward with this method.
So at the SKA here, we're putting a lot of effort into the robustness and continuity of the clocks that are used for the first order pulsar timing in SKA mid and low, actually. And so I'm just wondering what sort of errors you would incur if there's an interruption of these clocks for a while and they have to catch up. They track UTC, as you probably know, going through the satellite system, and there's some errors in there. But then if there's an interruption, they would have to resynchronize, and presumably your data sets can also cross a gap like that, but it might incur some errors. I'd just be interested to know what your
Yeah,
what you could say about that.
in general, it's been a while since I thought about this on an observatory side way of thinking. But in general, so long as you know what your offset is, things will be fine. The problem becomes so I grew up on Chime, and we briefly had a problem where when we restarted the system, we would get like weird 2.5 microsecond jumps, and that was a huge problem. But if you aren't having like strange jumps, you can predict what's going to happen. And you can track what's going on. We have a concept called clock corrections where we can add information about things that happened. We also have things called jumps, and different PTAs use them differently. But one of the ways you can do them is looking at offsets that happened at different times. We also have had some stuff like the Meerkat data, I believe, and some of the PTA data, some of the different data sets use GPS time directly. We've actually found that seems to be working reasonably well as well. So.
Okay, thanks, Deborah. We are going to move to the next talk.